So we're going to move on from chapter 9 now to chapter 10, talk about Mars, which is a very interesting place. And we'll talk about, as we did before, mention some of the features of Mars. Mars can be close to or away from the Sun. At opposition, its largest and brightest, when it's close to or away from the Sun, we call that a conjunction. So when it's at opposition to us, that's when it's away from us, it's actually at its brightest. And during the perihelion, when it's at its closest approach to the Sun, Earth is at 0.37 astronomical units away, and you can actually, using ground-based telescopes, you can actually resolve features on the surface of the planet only to about 100 kilometers across. There are two small moons known as Phobos and Deimos. And Phobos is the larger of the two moons. It orbits at 9,378 kilometers. And these are not round objects. They're, if you actually look at them, they're elongated. They're funny-looking objects. Phobos is 28 kilometers in diameter at one point, and 20 kilometers at its if you look at it as an ellipse, and it's certainly not an ellipse, but it's 28 by 20. Deimos is somewhat smaller than that. It's 16 by 10 kilometers. So these are kind of little things, but nevertheless they are visible using telescopes. They are visible from the Earth. And as I said, Phobos orbits at 9,378 kilometers, Deimos at 23,459 kilometers. The names of these moons are actually the names of the children of Mars, Ares, which is the Greek word for Mars. Phobos means fear, and Deimos means panic. So those are the two Martian moons. Phobos orbits Mars every 7 hours and 39 minutes, and both moons are probably captured asteroids. So it's a lot different than, say, the Earth's moon. So by using Phobos and the way that Phobos interacts with Mars itself, we can use that to actually calculate. We use Newton's law of gravitational attraction, and from this we know that Mars has a mass of 6.4 times 10 to the 25th kilograms. So it's 0.11 Earth masses. So it's and its density, as I mentioned, in correcting myself from what I said last time, is only 3,900 kilograms per cubic meter compared to the Earth, 5,500. So when I said in the previous lecture that all of the terrestrial planets had approximately the same density, and they go from, we saw that Venus was 5,200 and Mercury, I believe, was 5,400, so they were pretty close. But this one is a lot. Is certainly not. Is much less than the others. So only 3,900 kilograms per cubic meter. The core of the planet. This tells us that the core of the planet is not iron. It's got to be something that's lighter than iron, because we believe that studies that have been made so far indicate that it's got a fairly substantial core, but the core is probably an iron sulfide. So it could be, we don't really know, it could be FeS or Fe2S3, or maybe even something like pyrite, which is an FeS2. But the core, any of these things would have densities much less than that of iron itself. Sulfur being a much lighter element than iron, and this is the mineral pyrite, and these other things are the kind of things that we would actually see, and we do actually see these things not as sulfides but as oxides. We also see oxides of iron on the surface of Mars. So Mars is basically covered with a lot of pulverized rust. Again, either an iron ferrous oxide, or an iron 2 oxide, or an iron 3 oxide, and that's the actual surface. The rotation rate is very similar to that of the Earth. A Martian day is 24.6 hours long. And from the Earth, you can see, and this was observed, very easily with even relatively small Earthbound telescopes. But you can see that the planet seems to have at the poles, it's got ice caps. So at the North and the South Pole, there are ice caps. And the other thing that it seemed for a long time, looking at this from the Earth, was that we know that there seem to be seasonal changes on Mars. So these caps will wax and wane in terms of their size. They'll get bigger during the Martian winter, and they'll get smaller during the Martian summer, which seems to suggest that something is evaporating and then or at least melting and then recondensing later on. The polar caps are actually divided into two parts. So we have what's called a residual cap, which is the part of this cap that is permanently frozen. So this doesn't melt. So maybe a certain percentage of it is permanently frozen. And you have that on both surfaces. You have a residual cap. And then you've got the part that actually does melt. So you've got this seasonal cap that actually, as I said, that changes during the summer. It seems to melt. These are the caps themselves are composed principally of carbon dioxide, so they're actually dry ice. It's minus 120 degrees Celsius at the poles at the warmest time of the year, and that's why because the actual temperature at which carbon dioxide sublimes or changes from a solid to a gas is about minus 78 degrees. So this is cold enough to keep this in the frozen state permanently. But during the summer, the seasonal caps begin to evaporate. The northern cap is considerably warmer, and this seems to be due, even though the southern hemisphere of the planet is warmer than the northern hemisphere, the northern cap is warmer because there are these enormous dust storms that seem to be blowing the warmer dust from the south to the north. So that's actually cooling the south down and warming up the northern part. Now the northern residual cap, unlike the southern cap, apparently is composed of water, not carbon dioxide. So it's frozen water, and this is great news for Earthlings, because at some point in time we might want to colonize this planet. And if you had a situation where there was no water available, that would not be a good thing. But there is a lot of water, apparently, not only in the caps, but there also probably is water in the form of permafrost that's actually in the soil as well. But generally speaking, we don't see flowing water. It's in particular areas, or it's a certain distance underground, and the water that we would need to bring from the Earth would, if we were actually going to colonize, would make that would take up an awful large amount of space on board a spacecraft. We'd have to have a really huge spacecraft in order to transport enough water to actually enable colonization. But now we have a way, possibly, of if we can go to the poles, the North Pole, we can probably get water from that, and that would be a way that it might be possible at some point in time to actually colonize the planet. Mars has, if we look at the surface, it's got rolling volcanic plains and heavily cratered highlands compared to some of the other planets that we've looked at. The most notable feature on the surface of the planet is called Valles Marineris, and this is a really huge canyon. You could call it the Grand Canyon of Mars, but it would completely dwarf our Grand Canyon. It's 120 kilometers wide and 7 kilometers deep. Our Grand Canyon is only 20 kilometers wide and 2 kilometers deep. And it also runs a length of 4,000 kilometers, which is nearly the full width of the continental United States. So this is really an enormous, to me, to see something like this must be absolutely amazing to actually be standing at the top of this and looking down on it. Mars has the largest known volcanoes in the solar system. Olympus Mons is 700 kilometers in diameter, which is a little smaller than the state of Texas, and it rises to a height of 25 kilometers above the plains. The volcanoes are believed to be higher on Mars than they are on the Earth because of the lesser gravity, so that it actually enables the volcanoes to grow. Whereas on Earth, the higher gravity actually pushes a lot of that material down. It doesn't allow it to grow in a vertical sense. There's lots of impact cratering, and it's still much of this stuff is still visible. It hasn't worn away because the erosion rate on Mars is only 1% of that of the Earth. And there's a lot of evidence of ancient water flows, runoff channels in the Martian surface. And this has a very strong resemblance to river systems that we would see on the Earth. If we look at the crater ejecta, the material that's actually brought out from the impact of meteorites on the surface of the planet, we'll see that this is where we can actually see the permafrost. So the permafrost is a few meters below the surface. There's no liquid water that has been seen yet, and probably wouldn't be because of the colder temperatures. But the surveyor's craft actually photographed something that might have been a relatively recent flow of water in the form of a mudslide that froze when it hit the Martian surface. So it's not really, we'd have to actually, look at that up close to see what that is. The history of Mars, it probably had liquid water at one time, about 4 billion years ago. Mars's water froze, the atmosphere evaporated, possibly after impact with a large object, a large asteroid. And because of the weak gravity, and what we actually have on Mars is a reverse greenhouse effect, because we don't have that, even the small amount of carbon dioxide that we have on the Earth, we don't have that at all. So Mars would, because of the fact that it's further away from the sun, and also we don't have this greenhouse heating, that caused a lot of cooling. The secondary atmosphere that is actually present on the planet is only a little less than about 0.6% of what we actually have on the Earth. So it's 6 times 10 to the minus third atmospheres, and this was probably acquired by outgassing. That is that the rocks and the minerals that are actually present on the planet gave up some of their components from solar bombardment, and actually so we've got the atmosphere is mostly carbon dioxide, even though it's only a very, very tiny amount of carbon dioxide. That thin atmosphere is 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, only 0.13% oxygen. So although we could get oxygen out of the atmosphere, it would be a chore to do so, and there's not a lot of oxygen. So this atmosphere, even if it were much more concentrated, would not be able to sustain life as we know it. There's 0.07% carbon monoxide and 0.03% water vapor in the atmosphere.